Hello everyone, welcome to the first video of my custom RC F-16 build. We'll start the project off by walking through my Fusion 360 model of the plane, while I explain various design considerations like the plane's scale, materials, and functional characteristics of the full-size plane that I wanted to maintain in my scaled-down version. Before I started modeling the plane in Fusion 360, I had to decide on a scale for the project. I wanted to set the scale before modeling because that would allow me to model true to scale, and there's many benefits in doing so. First, it allowed me to incorporate items like the servos and the retracts to help me figure out where they'll fit, but most importantly, where they won't fit, or where I'd have to modify the plane's design to make them fit. If you spend the time up front in your CAD model to work out these kinds of details, it helps save time, money, and waste during the physical build, since it can eliminate issues that you'd otherwise come across that would require you to remake something, or worse, have to do a major redesign of the plane. I modeled watered-down representations of the electronics I plan to use. So you can see I have some servos, I have the speed controller, the receiver, the retracts, and the EDF unit. I didn't go crazy modeling them in complete detail because it's really only the major dimensions of the parts that you need to help with the design process. For example, let's look at the vertical fin and the rudder servo. As you can see, the vertical fin gets thinner as you move towards the tip. Having the servo modeled to scale helped me realize that I have to put the servo all the way down at the base of the fin in order for it to fit between the skins. Let's look at a cross-section. As you can see, it just barely fits between the skins. I ended up choosing a scale of 1/13, which equates to a 30-inch wingspan. And if you're familiar with EDF-powered RC jets, this is about the same size as a typical 70mm jet. I'm planning to 3D print a lot of parts for this project, like the exhaust nozzle, so having everything modeled to scale is pretty nice because it saves me from having to rescale the items manually in the slicing software before printing. I wanted the plane to be the smallest scale possible that would still allow me to incorporate retractable landing gear that are adequate for a grass runway, but also have an uninterrupted, fully functional inlet duct. The nose wheel I have is about 40mm in diameter, and the rear landing gear have a 50mm diameter wheel. I could have gone with the smaller scale plane while keeping these retracts, but the wheels would take up so much space inside the fuselage that it would make it really difficult to have an inlet duct that's functional and uninterrupted. And by uninterrupted, I mean that there's no weird protrusions into the duct because of the wheel. And there were two main reasons why I didn't want to go bigger than this scale. The first being I wanted to keep costs down on the electronics, because if you have a bigger power unit, you need a bigger ESC, then you need a battery, bigger retracts, bigger servos, and that all just starts costing more and more. Another reason is due to limited storage space I have at home. The majority of the plane will be made up of fiberglass and epoxy skins, supported by balsa wood or birch wood frames, ribs, and spars. All of the fiberglass skins will be made using the help of 3D printed molds. For example, this is one of the molds that I'll 3D print for the lower half of the nose. The plane will also have a bunch of 3D printed parts on it, which are all the parts that you see in blue, like the beginning of the inlet duct, the wingtip pylons, the ventral fins, the exhaust nozzle, some detailed intricate bits on the back of the vertical fin, and the fuselage trailing edge. Most of the wood parts are going to be made using balsa wood to keep weight down, but the main load-carrying frames and spars will be made out of 3/16 inch birch plywood. So most of the frames that you see here that are very thin are going to be balsa wood, while, for example, the two frames that support the nose gear are going to be thick plywood. The two frames that support the main landing gear and the spar of the wings are going to be plywood as well. And then the main frame that supports the horizontal stabilizer pivots and the main spar of the vertical fin, that frame is also going to be plywood. As I mentioned earlier, a functional inlet duct and retractable landing gear are two characteristics of the real plane that I wanted to maintain on my model. Many RC EDF jets on the market feature what are called cheater vents on the underside of the fuselage just before the EDF, which allow air to pass through and feed the EDF. I assume they have this because those models don't actually have fully functional inlet ducts, or if they do, they don't allow much airflow into the EDF due to obstructions from protrusions from the landing gear or battery compartment. I personally don't like the way cheater vents look, so I had to make sure to create an inlet duct that was plenty open to allow enough airflow into the EDF. Since I'm using commercially available retracts, I didn't really have any control over their shape and size. So what I had to do was first position the landing gears so that they are completely inside the fuselage when retracted, then build the inlet duct around them. To ensure a consistent and open passage to allow plenty of air to feed the EDF, I first measured the frontal area of the EDF unit, then made sure my inlet duct had at least that much cross-sectional area throughout its length. I'll show you what I mean by taking a cross-sectional cut and moving it down the length of the duct. Another characteristic of the full-size plane that I wanted to maintain was the full movable horizontal stabilizer, which means the entire horizontal stabilizer rotates about a single axis to control the pitch of the airplane. I'll accomplish this by gluing an aluminum shaft into each horizontal stabilizer that rotates inside 2 bushings attached to the fuselage. Then I'll have a set screw shaft collar to prevent it from sliding out. One thing to note is the importance of where the axis is positioned. It affects how hard the servo has to work to pivot the stabilizer when moving through the air. If the pivot point is too far forward or aft, the aerodynamic forces will cause a really large moment or torque about the axis. The servo would then have to counter that torque. There exists a sweet spot somewhere in between where the moments nearly balance out, making it so the servo doesn't have to work very hard to pivot the stabilizer. I've set the axis at 42.5% of the horizontal stabilizer chord at the fuselage, which is just a bit forward of the balance point I've determined for this stabilizer. I may post a future video showing the test I did to come up with that location. For reference, based on my measurements from pictures of the full-size F-16, they have the axis at about 45% of the chord. The final characteristic I wanted to touch on was having true-to-scale wing, horizontal stabilizer, and vertical fin airfoil thicknesses that also have relatively sharp trailing edges. Many commercially available RC planes are made up of mostly injection molded foam, which isn't very robust or stiff when it's really thin. I think that's why the trailing edges are often really thick, as seen here on my E-Flite Extra 300. Since I'll be using fiberglass composites, which are much stronger and stiffer than foam, I'm free to make the trailing edges nice and thin. From what I could find online, the full-size F-16 uses a NACA 64A-204 airfoil, which is really thin. The 4 indicates the airfoil is 4% as thick as it is long. I ended up using a NACA 64-206 airfoil for the wing, which is 6% thick. I chose this slightly thicker airfoil to give me a little bit more room to fit the aileron servos inside the wing. For the horizontal stabilizer and vertical fin, I used the symmetric NACA 16006 airfoil, which is also 6% thick. Thanks for watching. Please consider subscribing if you'd like to follow the rest of the build. In the next part, I'll be focusing on the 3D printed molds for the composite layups. I'll explain how I designed them, print settings used, and prepare the finished prints for the composite layups.